6. Number 27. A regular polygon is pictured. What is the sum of x and y? This is our ask. Sum of x and y. Sum means add together. So we need the measurement of angle x and angle y added together as our final answer. Let's go back to the beginning. It said it's a regular polygon. Regular means all the sides and all the angles are congruent. So I have 1, 2, 3, 4, 5, 6 sides for this polygon. N equals 6, that's the number of sides, which means it's called a hexagon. Just important information to know. Now, with a hexagon and with any regular polygon, what we can do is we can find something called the central angle. The central angle is what's formed the whole way around this shape. All of these are central angles. It's when you take the center of your shape, you connect it to each of the vertices and form a whole bunch of triangles. And in each triangle, the angle at the top is your central angle. You need that central angle to figure out how much you could rotate something by to make it look like it hasn't moved, to map on top of itself. So let's figure out the central angle measure. That's going to be one measurement we can get right away for one triangle, and then getting x and y is going to be easy. So central angle equals 360, because that's the full way around, that's a full rotation, divided by the number of sides, which is 6. 360 divided by 6 is 60. So that means that this angle at the top is 60 degrees. So getting x and y is going to be really easy, because we know that in any triangle, all three angles of a triangle add up to 180. So if all three of these angles add up to 180, we've already used up 60 degrees. Now we can figure out what's left for x and y together. In other words, the sum of x and y. So I'm going to take 180, I'm going to subtract 60, and I'm left with 120 degrees. So my answer for x and y together is 120 degrees. Quick and easy. Moving on to number 28. Number 28. Find the midpoint of line segment AB with coordinates of A at -6, 2 and B at -4, -5. Okay, now we can grab a piece of graph paper, but let's just do it the old-fashioned way with our midpoint formula. It says find the midpoint. So you've already written this on the back of your packet. It's something you have to memorize. Let's write it down. Try it yourselves before I write it down. x1 plus x2 divided by 2, y1 plus y2 divided by 2. In other words, you're taking the average of the x's and the average of the y's. Now let's plug in. Our x values are -6 and -4. So -6 plus -4 divided by 2. Our y values are 2 and -5. 2 plus -5 all over 2. Now notice I didn't even take the time to label x1, y1, x2, y2, because it doesn't matter. When you're adding, it doesn't matter. So let's simplify. -6 plus a -4 means I'm doing -6 minus 4, which is -10, divided by 2. 2 plus a -5, I'm subtracting 5 from 2, which means I'm at -3 divided by 2. Simplify one more step further. -10 divided by 2 is -5. -3 divided by 2, I could leave it like that, but if I want to plot something in a second, I want to see the actual coordinate as a decimal. -3 divided by 2 is -1.5. Okay, now I'm going to grab a piece of graph paper, you grab a piece of graph paper, and let's see if this answer makes sense, because this is such a simple question that if you miss this on the EOC, it's just because you didn't take the time to check. Okay, so here's my graph paper. Let me plot the original line segment AB. -6, +2. That's A. B is at -4, -5. B. Let me connect them. Okay, and now let's see if my answer makes sense. So that I figured out -5 and then -1.5. So it's a little bit more than just -1. So -5, -1.5. That's right around here. Now it's on my line segment. Looks like it makes sense. It looks halfway. So I'm happy with my answer. I'm going to stick with it. This is my midpoint. Now, if you ended up getting an answer that was, I don't know, over here somewhere, you know you did something wrong. And this is just a quick and easy check to see, well, was I on the right path or not? Let's move on. Number 29. In the following diagram, AB is congruent to GF, angle A is congruent to angle G, and AC is congruent to GE. We're going to show that the two triangles are congruent by applying the following algebraic descriptions that would map triangle GFE onto triangle ABC. Okay, so it's a two-step process. We know this because we see that they gave us two spaces where we have to fill in an algebraic description. In other words, we have to complete the transformation using algebraic descriptions, not just writing what happens, but writing it out in terms of an x, y becomes, and then what happens to the coordinates. Now, let's go over what they said in that first sentence. I'm going to zoom in, and I'm going to put all that information into my diagram. It says AB is congruent to GF. Okay, I'm going to put a tick mark. Angle A is congruent to angle G. I'm going to put an arc and another arc. And lastly, AC is congruent to GE. 2 ticks and 2 ticks. Now, they told us they want us to show that they're congruent using transformations and that they'll map on top of each other. However, we can see that these two triangles are also congruent because of one of our congruence postulates. Notice that it's actually side, angle, side. That's how we know that these two triangles are congruent. So we can definitely see some type of transformations that will take us from triangle GFE and turn into triangle ABC. Now, looking at it, it looks to me like there was a rotation and probably a translation after that. So this is a lot of visualization here. It looks like the triangle on the right, GFE, was rotated in this direction, about 90 degrees, I would say, probably a rotation of 90 degrees counterclockwise. And then whatever happened there, we probably had to shift it into position. So what we're going to do now is I'm going to take another little diagram, and you would plot this down onto your own graphs if you didn't have one, and we're going to physically rotate the paper 90 degrees counterclockwise, which means we're going to rotate to the left 1/4 of a turn, and we're going to see where do the coordinates of GFE end up after that turn. Once we have that, we'll see how much we have to shift once we have it rotated. So let me go get another piece of graph paper. I'm going to turn it, and we're going to look at the difference. Okay, so now here is my graph physically turned counterclockwise 90 degrees. Let's take a look at what each of the coordinates are now. So imagine that this is a brand new graph. Kind of ignore where the positive and negatives are, and let's read each point. So G is to the left 4, so it's -4, and then up to 6, so it's at -4, 6. That's G prime, because now it's been rotated. So it's a new figure. It's an image. F prime, it's at -2 up to 4. And lastly, E prime. E prime is at -7 up to 2. Okay, let's compare with the figure up top to see what's different between these two. Okay, so G is at negative 4, 6. Well, let's look at where it's supposed to be. G is supposed to turn into A. A is at negative 5 up to 7. Where was ours again? Let's take a look. Ours was at negative 4, 6. So what I'm going to do is I'm going to plot all of these points onto my graph. And I'm going to see how do I need to move to get it to fall directly on top of A, B, C. So negative 4, 1, 2, 3, 4, up to 6. That's right here. So this is going to be my G prime. Then I'm going to go to F. So F is located at negative 2, 4. Negative 2 up to 4. It says F prime. Oh, sorry, not there. I need to fix that. Negative 2, 4. It's right here. And lastly, E prime. E prime is at negative 7, positive 2. E prime. There we go. I'm going to connect all three of these points. And it looks like I'm very close to having the triangle fall on top of ABC. My last step is I'm going to have to shift this up 1, left 1. Up 1, left 1. Up 1, left 1. Okay, so 2 steps. I need to talk about the rotation 90 degrees counterclockwise. Then I need to talk about the translation up and over. Okay, let's talk. So I can't just write that I want to do a rotation 90 degrees counterclockwise. I have to talk about how the coordinates change. So what you need to do is you need to grab one pair of coordinates before and after and take a look at how they changed. I'm going to grab G prime and the original G coordinate. So G was originally located at 6, positive 4. After the transformation of a rotation 90 degrees counterclockwise, we're at G prime, which is at negative 4, 6. 6 was your original X value. 4 was your original Y value. Look how the 6 went to the back of the coordinate. So now X is in the back. The 4, which was your Y value, moved to the front and it changed signs. So I'm going to put that Y is in the front and I'm going to put the negative there. So this is my algebraic expression. X comma Y becomes negative Y comma X. So I'm going to fill that in. Negative Y comma X. Rotation done. Now the last thing that I need to show is that there needs to be a translation. We mentioned before, it's up 1 and left 1. Okay. Up 1, left 1. Well, I need to talk about how it moves left or right first because coordinates are listed with the X value first. So I move to the left 1. That's a negative movement. So I'm going to put negative 1 as to what we're adding to the X coordinate. Now in terms of the Y's, I moved up 1. That's a positive movement. So I can keep this as a 1. That's it. I'm done. Number 30. The mass of a steel bar is 63,890 kilograms. So mass is 63,890 kilograms. I'm going to write that down. Capital M equals 63,890 kilograms. Next, for 7.9 meters cubed, well, they didn't say what that is, but if I see meters cubed, I know they're talking about volume. So that means the volume of this steel bar is 7.9 meters cubed. What is the density of the steel bar to the nearest tenth? Okay, density. If you remember from the last question, we have a special little density triangle that we could use to figure out this answer. Now, even if you don't remember the density triangle, look at how they want your answer. Kilograms per meters cubed. In other words, kilograms divided by meters cubed. So that should tell you right away, all you need to do is take your mass, which is in kilograms, divide by meters cubed. And then you'll have that unit of measurement, kilograms over meters cubed. So let's go ahead and we're going to divide in the calculator, and then we'll talk about the density triangle. So 63,890 divided by 7.9 equals 8,087.34, yada, yada, yada. So we need to round to the nearest tenth. So our final answer is going to be 8,087 point, let's see how we need to round. Well, the 3 should either round up to 4 or stay at 3. I look next door and nope, it's going to stay at 3. So 8,087.3 kilograms per meter cubed. That's our answer. Now, if you use the density triangle, let me recap the density triangle. Density, mass, volume, DMV. In this case, we were trying to solve for our density. So it's telling you that what you need to do is take mass divided by the volume, and you'll get your answer, which is exactly what we already did. So even without the density triangle, we figured this out because of the way they gave us the unit. Kilogram over meters cubed. Let's move on. Number 31. Fill in the blanks below. Okay, it looks like we're doing trig. I see sine, I see cosine, but there's no diagram, and I don't have this as a calculator question, so I wonder what this is testing. Well, I'll tell you. It's called sine and cosine complementary functions. So I'm going to draw a fancy little right triangle here. Okay. See if this works. Perfect. Okay, so here's my fancy little right triangle. Now, what I want to talk to you about is if you have a right triangle, and we'll call this triangle A, B, C. A and B are always going to equal 90 degrees. They're always complementary. They always will equal 90 degrees. As a result, there's a fun little rule here. Sine of A will always equal the cosine of B, regardless of what the measurements of A and B are. So you'll notice in this rule, sine and cosine are those opposite functions, sine and cosine. And then A and B always have to add up to 90 degrees. We're going to use this little rule to come up with the answers for A, B, and C. Now, in the first one, you'll notice we have a sine and then a cosine. So that must mean that whatever we have here with the 25 and whatever we get as an answer here should equal 90. So I'm going to do 90 minus 25, and I get 65. So 65 cosine should give me the same value as 25 sine. Now I know this is a non-calculated question, but I just want to show you what happened. So in the calculator, I'm going to put 25 sine, and we get approximately 0.422. Okay, so I'm going to write that down. Approximately 0.4226. If I did cosine of 65, by this equation, it says they should be equal. So let's take a look. 65 cosine. 0.4226. Yeah, that's exactly the same thing. And that's just to prove to you that this law here, or complementary cosine sine rule, is always going to work. Now let's take a look at our next one. It's a little bit more tricky. So we have cosine of x equals blank, and they don't really give you anything else. Well, follow our rule here. Instead of sine, you're going to put cosine. So here I have cosine, so we're going to put sine. Now for your angles, they have to add up to 90. So if one angle's x, then to get the other angle, you're going to subtract x from 90. So we're going to write sine of 90 minus the x. Okay, last one. Cosine of 10 equals blank of 80. Well, notice 10 and 80 together equal 90. So they're following our little rule here. Instead of cosine, we're going to put sine. So the rule, switch your trig function and make sure that your two angles add up to 90. That's it with page 6.